What we want to do now is a few examples of each of the topics we've covered so far in Chapter 12. All right, so we're going to cover an example for electrostatics, the electric field, and then voltage. All right, so our first example, let's say that we have a charge. We have a charge of plus 3 times 10 to the negative 6 coulombs. All right. So this is a positive charge, and we have a charge of negative 6 times 10 to the negative 6 coulombs. All right, and let's say they're separated by a distance of 0.15 meters or 15 centimeters. So 0.15 meters. All right, and we just want to calculate the force that each of these objects exerts on each other, all right? And by Newton's third law, recall, all right? So by Newton's third, let's do it this way. So by Newton's third, the forces will be equal and opposite, all right? Equal and opposite. All right, so what that means is that if we call this Q1 and we call this Q2, all right, Q1 will pull Q2 this way since it's attractive, and Q2 will pull Q1 this way since it's attractive, and these two forces, all right, this pull and this pull, will be equal in magnitude but opposite in direction, all right, and that's simply what Newton's third law says. Right. So now we can set this problem up in equation form, right? So remember Coulombs Law says F equals K, Q1, Q2 over R squared. And we just plug in the information from the previous part. So remember K is 9 times 10 to the 9th, newtons times meters squared over coulombs squared. And here we're going to have I'm going to drop some zeros just for some space, but we're going to have 3 times 10 to the negative 6 coulombs times 6 times 10 to the negative 6 coulombs, and that's going to be divided by 0.15 meters quantity squared. All right. Now, you may be arguing right at this point that there should be a negative sign right here, right? And in all technicality, that's not necessarily the case, all right? So we can erase that negative sign, all right? But what we do need to keep in mind is that the force will be directionally dependent. Now, the reason we can ignore that negative sign is many books oftentimes write Coulombs Law like this, all right, where we have the absolute value of our charges, okay, and then it's up to you to determine which direction, okay, let's call this force 1 and call this maybe force 2, all right, and again, remember they're going to be equal, but then it's up to you, the problem solver, to determine which direction the force is in. All right, and that's going to be based on whether or not the charges are attractive or repulsive. Okay, but we can, for our purposes, we can maybe consider this that we're finding the magnitude of the force. All right, so our goal is just to find the magnitude. The magnitude of F. All right, and that's what this expression here is, and that's why I'm going to drop the minus sign. All right. Okay, so now that that's all set up, you can just plug this into your calculator, and luckily enough, this all boils down to a very nice number. This is just 7.2 newtons. All right, so it's just 7.2 newtons, and then again, it would depend on if we are looking at the force on Q2 from Q1, or if we're looking at the force on Q1 due to Q2, as to which direction things would be moving. All right, but that is the magnitude. All right, okay, so that's our first problem. All right, and our second problem, okay, let's imagine that we have a charge of 2.0 times 10 to the negative 6 coulombs, right? So this is a positive guy. And it experiences forces from two other nearby charges, all right? So we have another charge here and maybe another charge here. And a 14 Newton force is to the east. Okay, so this means we have to set up a coordinate system. So I recommend we just make a normal coordinate system here with east to the right and west to the left. And so what this is saying is that this charge, whatever it is, and by the way, if it's exerting a force this way on the positive charge, it must be negative. This is going to be 14 newtons to the east, right? And we have another charge over here that is putting a 10 Newton force to the west. So this arrow will be not quite as long. And this is going to be 10 newtons, right? And our goal is to calculate the value of the electric field at our charge. All right? So we want to calculate the value of the electric field at this charge right here. Okay? So, how do we do it? Well, first things first, remember that the electric field is equal to F over Q. And we got this, remember, from F equals QE. All right? So this is a second way, sort of, to write Coulomb's Law, only in terms of the electric field instead of all of the K, Q1, Q2 over R squared business. All right? And so this means our step one, we need to find the net force, and then step two, use above formula. All right, so those are our steps. So let's go back here, and we notice that here we have a 14 Newton force to the east, and here we only have a 10 Newton force to the west. So what is our net force? Right? What is our net force? Well, what we can do is say that our net force, or sometimes this is written as F net, is going to equal the sum of our other forces. All right, so call the eastward force F1 and the westward force F2. All right, so this is going to be 14 newtons plus 10 newtons. But now we have to take into account the direction. So this guy was east, this guy was to the west, and so they're going to oppose each other. All right, and if we take the typical convention that right would be positive, then that means west is negative, and we have to insert a minus sign right here. So this guy is going to get tugged to the east with a total force of 4 newtons. All right, so before we move on, let's just make sure we understand what this is saying. This is saying that if I pull something with 14 newtons to the east and 10 newtons to the west, then this is no different than pulling it with one force of 4 newtons to the east. All right? It is no different. Okay? So now we have our net force, and now we can plug it into our formula. E equals F over Q, and F was 4 newtons, and Q was 2 times 10 to the negative 6 coulombs, and this gives us 2 times 10 to the 6th newtons per coulomb. So that is the value of the electric field at the charge that we were interested in. All right, so that's the value of E at Q. All right, so that's the value of E at Q. And lastly, okay, our last example, we want to have a potential energy problem. And so here we have a charge, of 5 times 10 to the 6th coulombs, negative 6 coulombs. All right, and its potential energy decreases from 0.29 joules to 0.04 joules when moved from some point A to point B. All right, so when moved from point A to point B. So let's visualize the situation here. One way that a charge will experience a change in potential energy is to put it inside of a uniform electric field. So let's start there. All right, and again, we've already seen how to make a uniform electric field, and I'm going to make 2 plates, and on the top plate we'll put all sorts of positive charge on it, and on the negative plate we'll put some negative charge. And remember that our field lines are going to be downward, like so. And here we have our plates. All right. So imagine that point A is right here, and that point B is right here. Now remember that if I have a positive charge here, it's going to naturally want to fall down toward the negative plate. All right? So that means that this is a high potential at point A, and B is low potential. And another way of thinking that is that point A has high potential energy, and B has low potential energy. And again, this is basically the same thing as the box that we lifted up in the previous video, and letting it fall. If you lift up the box, you're increasing its potential energy gravitationally, and once you let it fall, it's going to release all that gravitational potential energy. So here, it's going to have high PE, and down at point B, it's going to have low PE. All right. So if we put our charge here, we know that the value of the potential energy at point A is 0.29 joules, and at point B, it's 0.04 joules. All right? And we want to know what is the potential or the change in voltage. All right? So what is the change in voltage? That's the whole point we want to solve here. All right? So what is the change in voltage? Well, remember that delta V equals delta PE over Q. All right? So Q is going to be the 2.6 times 10 to the negative 6 coulombs on that guy, and this will be PE initial, or PE1, and this will be PE2. All right? So remember that delta PE is equal to PE2 minus PE1. So this equals, well, I'll not solve that yet. We'll look at the algebra first. All right. So delta V is going to be equal to PE2 minus PE1 divided by Q. All right, and delta V is what we're solving for, so our equation is already solved. Now all we need to do is plug in, and this will allow us to only need to use our calculator only one time. All right, so let's plug in, and when we do this, we're going to get PE2 is 0.04 minus 0.29 joules divided by 2 times 10 to the negative or I'm sorry, this is 5 times 10 to the negative 6. So 5 times 10 to the negative 6 coulombs. And when you carry out that calculation, we get a change in voltage of negative 5 times 10 to the 4th volts. All right. So this particle, this collection of charge, experienced a change in voltage of negative 5 times 10 to the 4th volts. All right. And again, that's determined by the potential energy that it lost. All right. Okay, so that wraps up this chapter. The next video will start to focus on Ohm's law and circuits. We will see you then.